Hi, and welcome back, everybody. It's time for video 3 of lecture module 3, and I actually have to pick up. I forgot to talk about why the sky is blue in the previous video, so I'm just going to do it here in video number 3. Let's go ahead and pick up where we left off then, and let's talk about why is the sky blue? So a lot of people actually think that the sky is blue because it's reflecting the color of the oceans. This is not correct. The oceans are blue for the same reason that the sky is blue, which is the scattering of light, specifically Rayleigh scattering of light, which ends up being wavelength dependent, such that blue light is scattered more than any of the other colors of visible light, meaning that blue light is just bouncing around everywhere, so no matter what direction you look, you have blue light hit it, blue photons, blue wavelengths hitting your eye, so the sky looks blue. Uh, so let's go ahead and take a quick look. I just love this image, so I do want to take a little bit of time. And also it shows that that the atmosphere can't be blue from reflecting ocean water, because here are clouds at the top of our troposphere. So you can see the top of our troposphere right here. And then here in the stratosphere, you can see the sky is blue. Here's the moon in the background, and outer space is black. So it's clear that something about our atmosphere is making it appear to be blue. We know that air is colorless because if you look around, you don't see any color in the room. So there must be some other effect that's making our sky appear to be blue. And really, this comes down to the scattering of light. So let's talk about what scattering is before we talk about the specific type of scattering that is responsible for making our sky blue. So the scattering of light is here you have a photon coming in. It's going to find a particle of atmospheric gas, whether it's a molecule or an atom. So here comes the light. It's going to interact with that molecule. And the way that it interacts is it's going to then leave in a random direction. So it comes in and then it gets scattered into a different direction. So that is what scattering is. It's light coming in from one direction, interacting with something in the atmosphere, one of the molecules or atoms, and then leaving in a random direction. What's critical about this and why the sky is blue is that not all wavelengths of light are scattered equally. Uh, so how much light is scattered depends on a couple of things. And the big one is it depends on the wavelength of light. It also depends on the size of the particles that are doing the scattering. We are talking about molecules and atoms whenever we talk about things in our atmosphere for the most part, which are all much, much, much smaller than the wavelengths of light, which is kind of incredible considering that light is on the order of hundreds of nanometers. But since all the atmospheric gas particles are about the same size, then we're not going to worry about that part. So let's focus on the wavelength part. And in general, the amount of light that is scattered is inversely proportional to the wavelength of light. So here we have another inversely proportional thing. As you go to smaller wavelengths, so as you go to shorter wavelengths, the amount of light that is scattered goes up. As you go to longer wavelengths, redder light, the amount of light that is scattered goes down. So what does this mean? It means that our longer, redder wavelengths are scattered less. They pretty much go straight through our atmosphere and don't get scattered around a whole bunch. Our shorter, bluer wavelengths are scattered more. They have a lot of trouble just coming straight through our atmosphere. They're going to interact and get scattered by the gas particles in our atmosphere, sending them so they're bouncing around everywhere. So blue light is going to be scattered more than red light. Now, specifically, what kind of scattering is happening in our atmosphere? And this is the answer to the question is, why is our sky blue? The sky is blue because of Rayleigh scattering. And this is the type of scattering that occurs whenever your particles are much, much, much smaller than the wavelengths of light. So if you're talking about like molecular nitrogen and oxygen in our atmosphere or argon. So all of these very, very small things, have sizes much smaller than the wavelength of light. So the type of scattering that occurs is what we call Rayleigh scattering. And it works just the same as what I was describing, that the blue wavelengths are scattered more than the red wavelengths. They get bounced around in the atmosphere more. Except it's a little bit extreme because for Rayleigh scattering, the amount of light that is scattered is not only inversely proportional to the wavelength, it's inversely proportional to the wavelength raised to the fourth power. So blue light is scattered a lot more efficiently than red light, which means that blue light in our atmosphere is scattered all around, while red light is not scattered very much at all. So it doesn't matter which way you look, as those scattering events send blue light to our eyes from any different direction. Any way you look, the sky is going to look blue. And this is why the sky is blue. Now, pictures are much better than a bunch of words, so I tried to create this wonderful slide. I upped my PowerPoint skills with this one. I even made a person with a hat. If you zoom in on the slides that are available to you on Canvas, you'll notice that the person even has a shadow. So let's take a look of how this works. So I am modeling the air particles, the molecules in air, mostly nitrogen and oxygen, N2 and O2, as just these gray spheres, these gray circles. And we're going to send in white sunlight. So we have visible light from the sun coming in. It's a mixture of all the colors of light. So that would be white light comes into our atmosphere. And then we're going to let this Rayleigh scattering process come in. So here I've represented all the colors of light. I've just spread out them into their spectrum. So we have red all the way over here to violet. So the light comes in. These wavelengths, the bluer wavelengths, are going to be scattered much easier than these ones. So they're going to get scattered and they're going to bounce around between all of these different air molecules as they're scattered about, removing them from the white light. So this person down here, if they look over in this direction, here comes some blue light hitting their eyes, so it looks blue. From over here, it looks blue. From over here, it looks blue. Pretty much everywhere they look towards the sky, it looks blue. So the sky looks blue. However, if this person looks at the sun, never do that directly. Do not stare directly at the sun. It is a bad idea. But if you were to safely look at the sun, it would have the bluer wavelengths removed, giving it an overall yellowish hue, which is why our sun looks yellow from Earth's surface. From space, it would look much closer to white. All right, so now that we've covered the rest of video 2, let's go into video 3 topic. So this is atmosphere part 3. We need to do our surface heating, and we need to talk about the temperature of the Earth. We have to talk about the greenhouse effect. So this is going to be a little bit of a long video, so go ahead and strap in. If you need to take a break, go ahead and pause, take a break. And when you come back, we are going to launch into how planetary surfaces heat up. This is what's driving the convection in the troposphere. We're going to define what's called the thermal equilibrium temperature, the temperature that we expect planets to be based on how far away they are from the sun, so how much sunlight they receive, and how much sunlight they absorb versus how much they reflect, their albedo. And then we're going to describe the greenhouse effect. And actually, you might not like that word, or it might be a word that you now has a negative connotation, but the greenhouse effect in general is a very, very beneficial thing. Without it, we would be a frozen Earth. And then I want to introduce a general planetary science concept to internalize all of this and give you some good conceptual questions so I can see how well you're internalizing this information for quizzes and exams. All right, so let's talk about surface heating. How does our atmosphere get warm? How does the surface of our Earth get warm? And what we need to do is we need to consider energy. We need to consider the energy that's going into the surface of the Earth and the energy that's leaving the surface of the Earth. If everything is in balance, the amount of energy entering Earth's surface should equal the amount of energy leaving Earth's surface. This would be a thermal equilibrium, as we call it. So let's look at each part. What is our energy coming into the Earth's surface? So where do we warm up from? Well, sunlight, of course. So here comes sunlight streaming through space, then through our atmosphere, and then hitting the surface of the Earth. Earth has an albedo of 0.3, which means that it reflects 30% of the light that hits it, pew, bounces back to outer space, and it absorbs 70%, depositing that energy into the surface of the Earth. We can also, so we know how much of Earth's surface what percentage of sunlight it'll absorb versus how much it will reflect. It'll absorb 70%. But we also need to consider that we are a full astronomical unit away from the sun, about 100 or about 1.496 times 10 to the eighth kilometers, 150 million kilometers, 93 million miles away from the sun. So that's pretty far away, which means that by the time that the sunlight from Earth reaches us, how much energy is going to hit each patch of ground, each square meter of ground? At the top of our atmosphere, we receive on average about 1,361 watts per square meter. That's a pretty light bulb, a pretty bright light bulb per square meter. But that's how much energy is coming in and hitting the Earth given our distance away from the sun. This number, by the way, is a very, very important number if you want to understand atmospheric physics or if you want to understand climate change. This is what we call the solar constant. It's the amount of sunlight energy that the Earth receives on average. And 70% of this will be absorbed by Earth's surface, 30% will be reflected back to outer space. So that's our energy in. What is our energy out? Well, the Earth is absorbing the sunlight. The Earth's surface is effectively a black body, very, very close approximation to a black body. So it absorbs all the energy that comes in, warms up, and then re-radiates that according to its temperature. Thank you, going over spectroscopy and spending all that time talking about black bodies. We know that given how much energy is coming in and the surface temperature of the Earth, that most of this energy is going to, most of this black body radiation back out is going to peak in the infrared. So we send sunlight energy in, it gets absorbed by Earth's surface, warming it up, and then we send the energy back out as infrared radiation, primarily. And these will reach a balance, and you can calculate what temperature is associated with that, and we would call that the equilibrium temperature. So again, since there are a lot of moving parts right here, what's warming us up, the energy in, is from sunlight. How much sunlight do we receive? Well, that is our solar constant, but then we also have to consider our albedo, which means that 30% is going to be reflected, leaving 70% to be absorbed. So that's our energy in. Our energy out is going to be determined by our thermal radiation laws. We could actually calculate this out, how much energy out, what is the radiative flux out from the Earth? Well, that's the stuff on Boltzmann law. So you could go ahead and use that the radiative flux out is equal to the Boltzmann constant times the temperature to the fourth power. So we want, these things are in balance. You set the energy in equal to the energy out, do a whole bunch of fancy math. It's a really cool equation, but I'm not going to blow everybody's brains by putting it up here on the slide. But you can solve for the temperature where the energy in equals the energy out, where the temperature is in balance, a thermal equilibrium as we call it. And that's going to define what I call our expected temperature, formerly called the equilibrium temperature. So you do all the math for the Earth, and what do we calculate? What is the surface temperature we should expect for the Earth based on how much sunlight we receive, how much we absorb, and then re-radiating that back out? Where is that balance point achieved? At 255 Kelvin. Now I know, the Kelvin scale, probably still not used to it. Let's put this into something more familiar. Negative 18 degrees Celsius is Earth's thermal equilibrium temperature. That's 0 degrees Fahrenheit. That's friggin' cold. That's really, really, really cold. In fact, at that temperature, we should be an ice ball. There should be no liquid water on Earth. There's got to be something else in play that makes the Earth warmer so we can have liquid water on our surface. And that is going to be the greenhouse effect. So without the greenhouse effect, our thermal equilibrium temperature tells us that the Earth should be an ice ball. We're clearly not. So we need a thermal blanket, something that actually raises our temperature back or up above what we expect. And this is going to be our greenhouse effect. And if we're going to talk about the greenhouse effect, we better talk about what is driving it, and that is greenhouse gases. So greenhouse gases, what defines a greenhouse gas? A greenhouse gas is any molecule, any gas molecule in a atmosphere, but in our atmosphere, that very efficiently absorbs infrared radiation. Remember, the Earth is trying to re-radiate all the energy that it's receiving from the sun back to outer space, mostly in the infrared. If there are particles of gas in the atmosphere, atoms of gas or molecules of gas that are very, very good at absorbing infrared radiation, then that infrared radiation will get absorbed, and then whenever it's re-emitted, it's either going to go back down to the surface of the Earth or up to outer space, thus creating sort of a thermal blanket. So any gas that's very effective at absorbing infrared radiation and then re-radiating it back down to the surface of the Earth is what we call a greenhouse gas. What are some major players? What are some major greenhouse gases? So water vapor is a very strong greenhouse gas. Methane is a strong greenhouse gas, and carbon dioxide is a greenhouse gas. But rather than me just telling you this, I want to show you this as well. And I want to go ahead and use some of the information that we've gathered, some of the skills that we've mastered to really show this. And that's what's going on in this plot down here. So here we have the wavelength of light. These are in microns, micrometers. So visible light would be way over here. And then here we have transmission of light. So anytime the transmission dips down, that would be absorbing that light, absorbing that energy. So these are absorption features. We are looking at an absorption spectrum. And this is an absorption spectrum of our atmosphere. And let's focus on things like this. We have this big absorption. So water absorbs lots of infrared radiation. Here we have a carbon dioxide. It absorbs a lot of infrared radiation right around the 14 to 16 micron region, which is very close to the peak blackbody temperature, the peak wavelength that we calculate by Wien's law for Earth. So CO2 is going to be very, very good at absorbing outgoing infrared radiation, and so is water, sending that back down to Earth. So now we can talk about the greenhouse effect. We have greenhouse gases, which are molecules that are very good at absorbing this outgoing infrared radiation. We've even leveraged and looked at this spectroscopically. So we've looked at the spectrum of it, and we understand all of that physics very, very well. This is just what these gases do. If you remember when we talked about molecular spectroscopy, we have these bending and stretching, these vibrational modes of molecules that were very, very good at absorbing and emitting infrared light. So we have these greenhouse gases in our atmosphere. The sunlight comes in, warms up the surface of the Earth, and then it gets re-radiated as infrared, which without any greenhouse gases would just go, make its way to outer space, no problem. But with things like carbon dioxide in our atmosphere, that carbon dioxide is going to absorb the wavelengths of light it likes. So it's going to absorb that infrared radiation. And once it absorbs it, what goes up must come down. It went to a higher energy state, it's got to go back to a lower energy state. So as it goes to a lower energy state, it's going to re-emit that infrared light. And whenever it does so, it does it in a random direction. Maybe it goes up to outer space. Maybe it goes down and gets reabsorbed by the Earth. So you have about a 50% chance of going back down and hitting the ground somewhere, and a 50% chance of going back up, where it could either run into another greenhouse gas molecule, or it could escape to space. So a infrared photon comes out, gets absorbed, 50% chance to go back down, 50% chance to go back up. So how much total will end up going back down depends on how many greenhouse gases are in our atmosphere. More greenhouse gases, the higher likelihood that those photons are going to end up going back down to the surface of the Earth, warming it up. This is sort of a thermal blanket. The infrared radiation leaving the Earth's surface is getting absorbed by greenhouse gases and then going back down. Acts very similar to how a blanket makes you warm. Your infrared radiation of your body is leaving your body via light, hits the blanket, gets absorbed by it, traps it in there, reflects it, keeps it in. Although this is a absorption and re-radiation. So with more energy going into the surface of the Earth, that means that we have to re-look at our energy balance. Our energy in and our energy out. Now our energy out is not as great because some of it is just getting put right back into the Earth's surface. So how much is going back down into the Earth's surface, what temperature that translates to is going to make things warmer. So it's going to push things up past our equilibrium temperature, past our expected temperature. So with the level of greenhouse gases we have in our atmosphere, the greenhouse gases warm up the surface of the Earth by an additional 33-ish Kelvin. So this amount of warming, this additional warming that we have, this additional energy factor, is called the greenhouse effect. It's an effect that raises the temperature past our expected temperature. So let's go ahead and put our 33 Kelvin onto our expected temperature of about 255 Kelvin for the Earth, 0 degrees Fahrenheit. That'll raise us to an average temperature on Earth of about 288 Kelvin. Again, not too familiar with the Kelvin scale, so let's go ahead and put those in familiar terms. 15 degrees Celsius, that sounds kind of nice, which is about 58 degrees Fahrenheit on average, a nice sort of brisk temperature where we can clearly have oceans and liquid water on the surface because that's above the freezing point of water. So our greenhouse gases generate a greenhouse effect, which is making it so Earth's temperatures are making Earth a habitable planet. Kind of cool, right? Thank you, greenhouse gases. So this greenhouse effect is actually very, very beneficial. The thing that we're really going to have to consider is what happens as we put more greenhouse gases into the atmosphere, things like carbon dioxide. Because physics is physics. Those greenhouse gases are going to be very efficient at absorbing infrared radiation in their absorption features, those absorption lines. So as we put more in there, we're going to increase this greenhouse effect. And the real big question becomes, is what's the response to the energy balance and how does that play out? So that's something that we're going to pick up, a very weighty topic. In the next video, we're going to talk about anthropogenic climate change. So I do want to end. I will leave, well, no, we'll go ahead and walk through these. So if you need to take another break, take another break. Stretch it out, come back. I want to give you an example question. Yes, this will be a question that will be appearing on quizzes and exams, so make sure that you master this material. And it is what I call a general planetary concept type question. And with this one is I'm going to give you a bunch of planetary data, things like the mass, rotational period, expected temperature, real temperature, just a list of properties of different planets. And then you're going to have to answer questions about that. In this specific case, we're going to answer the question, does our imaginary planet, does our generic planet have an atmosphere? Based on planetary data, can you determine which one certainly has an atmosphere or which ones certainly have an atmosphere? So let's run through an example. And yes, I did make this imaginary planetary system while I was very, very hungry. So I created the sandwich star system. So here's our sandwich star. And then we have 3 planets in the sandwich star system. We have planet BLT, planet Reuben, and then my personal favorite, planet chicken salad, which, yeah, I think that would be a good restaurant chain. So if in the future you see a restaurant chain called Planet Chicken Salad, where you can buy these nice round sandwiches, so bread on the outside in a spherical shape with chicken salad in the center, yo, I started that. So the data that I'm giving is the mass, the rotational period, the expected temperature, and the real temperature. So if I want to go through and determine whether or not BLT, Reuben, or chicken salad has an atmosphere, what I want to look for is the greenhouse effect. I want to go ahead and look at the real temperature, what it actually is, versus what we expect it to be, that equilibrium temperature. If the real temperature is higher than the expected temperature, that's evidence there must be greenhouse gases in an atmosphere to create a greenhouse effect. So if you can detect a greenhouse effect, then those greenhouse gases live in an atmosphere and you can conclude that that planet has an atmosphere. So let's go ahead and take a look at the data. So the data I'm interested in is the expected temperature versus the real temperature. And I want to see if the real temperature is higher than the expected temperature. So planet BLT, they're the same. No evidence of a greenhouse effect. Doesn't necessarily mean that there's not an atmosphere, but if there is, there's 0 greenhouse gases in it, which is kind of absurd to think about. But we can't say for certain that there is an atmosphere. And we're looking for the planet where we are certain there is an atmosphere. Let's go to planet Reuben. Real temperature equals the expected temperature. Can't really say here either. Planet chicken salad. The real temperature is a full 45 Kelvin greater than the expected temperature. That's evidence of a greenhouse effect. Chicken salad has an atmosphere. So I would conclude that out of all of these, planet chicken salad is the only one where I can conclusively say has an atmosphere due to a greenhouse effect. All right, so that ends video number 3. Make sure you master these questions, and I will see you on a weighty topic, anthropogenic climate change, in the next video.